Hi, everybody. My name is Diako. I'm a PhD student in chemical engineering. Today, I'm going to talk about one of my research, improving anti-fouling property of alpha-alumina tubular membrane by using ALD or atomic layer deposition for treating real produced water. First, I'm gonna start by giving a little bit background about what's the produced water. Produced water is a kind of brackish waters from underground formation that are brought to the surface during the drilling. And during the presentation, I'm going to address how can we deal with the produced water using membrane filtration, how can we fabricate an fouling resistant membrane for treating produced water, and how can we fabricate an applicable candidate membrane for industry. Here is the problem statement. On the left side, the blue and red dots are earthquake frequency across the whole Oklahoma state. The red spots are from 1882 2008, and blue spots are earthquake frequency from 2009 to present. And as you can see, the blue spots are increasing. On the right side, this is a map of water shortage prediction. As you can see, the west of Oklahoma will be facing drastic water scarcity in 50 years. That's why we need to think about treating produced water. Produced water is useless inherently, and we cannot drink it, we cannot swim in it, we cannot even use it for agriculture. And based on the last research conducted in Harvard University, if we could treat just 30% of the produced water, we can save all the basins, 205 basins in the United States. That's why we need to think about treating produced water in order to tackle this issue, water scarcity issue. Here is the produced water analysis. In our research, we are focusing on TOC, total organic carbon, total dissolved solid, total suspended solid. And TOC, produced water is heavily depends on geography in terms of TOC, TDS, and TCC. And here on the third column, you can see the EPA regulation for drinking water and agriculture. TDC is the summation of these elements, and I'm going to use this terms over and over in my presentation. That's why I want you just the TDS is just the summation of these elements. Membrane driving force. In order to work with membrane, we need a driving force. We have pressure, concentration, temperature, and electrical potential as a driving force in membrane. And always we have flow from phase 1 to the phase 2 from low end pressure, concentration, and temperature. That's why we can take advantage of the membrane technology for filtration process. If we categorize membrane in terms of morphology, we have porous and non-porous membrane. In porous membrane, you can see this structure. It has a porous structure. For non-porous, this is a very dense structure, and we use non-porous membrane just for gas separation. And for water and wastewater treatment using membrane technology, we want to focus on porous membrane. Porous membrane are mainly used for water and wastewater treatment. If we divide in membranes in terms of material, we have inorganic and organic. Inorganic like ceramic and carbon-based membranes. Organic like polymeric. Inorganic membranes don't swell. They have a uniform structure. They are chemically resistant, thermally stable, but they are expensive and they they're not flexible at all. Unlike an organic membrane do swell. They don't have a uniform structure. They are not chemically and thermally stable and resistant, but they are flexible and they are inexpensive. Here is how a membrane process works. Once produced water reaches the surface of the membrane, water does pass through the membrane. However, pollutants such as oil, salt, and heavy metals doesn't pass through the membrane and filters out by the membrane. And then the clean water collected in a storage tank. We evaluate membrane performance in terms of rejection rate and flux. Rejection rate is 1 minus concentration and permeate site here. Here, over concentration and feed site. And flux is the volume of water which passes through the membrane over the active surface area of the membrane times the time which is needed for this process. That's how we can evaluate a membrane process. Research objectives are improve the task 1, improve the pristine alpha-alumina membrane by coating zinc oxide using atomic layer deposition technique. Characterization of the zinc oxide ALD membranes, study the anti-fouling property of the prepared membranes. Here is how atomic layer deposition works. ALD is a unique technique in order to coat a thin, a uniform layer on surface. Here we use pristine alpha alumina, and by taking advantage of this reaction, we coated a thin layer of the zinc oxide. By manipulating cycles, we can change the thickness of the zinc oxide. Here is our membrane. The first one is pristine alpha alumina. Pristine alpha alumina. It's a disc with 1 inch diameter, 1 millimeter thickness, and the porosity is 25%. Okay, and then we modified these membranes by coating various cycles of zinc oxide, various thickness of the zinc oxide from M1 to M6. As you can see, for M1, 20 cycles, the thickness of the zinc oxide is 0.8 nanometers. From M1 to M6, rationally, the thickness of zinc oxide increased and it reached to 12.5 nanometers. Here's our setup. We call it flow-through system, okay? The surface of the membrane, the modified surface, touch the produced water, okay? Here, the zinc oxide layer. The pore size of this membrane, the modified membrane, are not small enough to reject salt. Just by increasing hydrophilicity, we could remove oil component. In order to remove salt, we installed a vacuum pump. Then, by starting the pump, the pure water evaporated and then collected in a cold trap here. But since the salt component don't evaporate it, all of the salt component stay above the surface of the membrane here. That's how we treated produced water. And here you can see the operating temperature in a room temperature, time of each operation 1 hour. And here you can see the delta P. In our case, the driving force is delta P, pressure. Here's the characterization of zinc oxide ALD membranes. Just here I showed just M0, M4, and M6. As you can see, by increasing ALD or zinc oxide, by increasing thickness of the zinc oxide, the pore size of the membrane decrease. For example, for A1, there is just 0 pore size between 100 to 150. But for M6, since the zinc oxide thickness increase, the pore size between 100 to 150 increased to 6, which means the pore size of the membrane decreased. Here is the EDS for M0 and M6 before separation test. On the left side, this is the the EDS beam detected oxygen and alumina, which is rational, which is what we expected because alpha alumina has a huge amount of alumina and oxygen. But after coating zinc oxide, we expected to detect zinc because of and oxygen because of, and here as you can see, the zinc appeared on the surface of the alpha alumina, and this red colors belongs to the zinc here. So we detected zinc oxide after capturing EDEX. Here is the oil contact and water contact angle. Alpha alumina is inherently hydrophilic because once we drop water on the surface of alpha alumina, water is spread out completely and water contact angle is 0. But in order to compare them, we needed to measure oil contact angle. Here we measure oil contact angle. From M0 to M6, oil contact angle increased from 165 to 170, which means by coating zinc oxide, we gave hydrophilicity property or water infinity of the modified membrane increase, which is a good point, ideal point for us. Here is the roughness. Okay, we expect to by coating zinc oxide, we expected to decrease roughness. This is a also ideal point for us because we can, by decreasing roughness, we can improve anti-fouling property of the membranes. How? Because in this case, there is no space for contaminant to deposit on the surface of the membrane. Okay, and here, as you can see, for M0, the roughness is SA is average roughness. SQ root means square height, and ST is the height differences between the highest peak and the lowest valley. For M0, the SA is 509, and the roughness then reach 332, which means by coating zinc oxide, we could decrease roughness of the membrane. Here is the AFM images for roughness. As you can see, for A, which is M0 to M6, the roughness decrease. Here is the important plot for us. The blue is rejection, TOC rejection rate, total organic carbon, and for the red line is a flux. For flux, first, for all the modified membrane, flux is higher than pristine membrane on M0, which is a good point, which means the modification process, the modified process work. Here then, the flux reach from 150 roughly to 190, and then it decreased a little bit, slightly. For TOC rejection rate, since we increase hydrophilicity or water affinity of the water, the TOC and in this case, all components cannot couldn't stick on the surface of the membrane. And because we increase water affinity, the TOC rejection rate increase from 96.5 to 99 for from M0 to M6. Here is the TDS rejection. The produced water had like 300,000 ppm, which is too salty. Okay. By applying M0, the TDS reached 53,000. Again, this water is not good enough. This treated water is not good enough for agriculture or drinking water. After using M1, the TDS reached 29,000. Again, it's too salty. It's not good enough for agricultural purposes, for drinking water, and for livestock watering. But from M2 to M6, the TDS reached 28, which means in this case, in terms of TDS, the treated water met all EPA requirement for agricultural purposes. Here's the question: why, by increasing ALD zinc oxide, by increasing ALD cycles, the TDS decreased immensely? The reason is we can explain by this. Because of the fractional free volume. First, we calculated water uptake in order to talk about fractional free volume. We need to calculate water uptake. What's water uptake? Water uptake, first we immerse the membrane inside the water for 48 hours, and then the membrane was the membranes were taken out, the membrane surface was washed, and then we calculate the weight of the membrane. We call it W2. Okay, W2 is the weight of the membrane, and then the membrane, we dry the membrane overnight at 40 centigrade inside the oven, and then again we took out the membranes, we weighed the membranes, and we call them W1 is the dry weight of the membrane. In this case, W2 minus W1 over W1, we could calculate it water uptake. As you can see, from M0 to M6, water uptake increased. It's because first, we gave hydrophilicity property or water affinity to the membranes. And because of the water uptake, the fractional free volume increased, which is because of the fractional free volume, this support the assumption of the hydrated salt being solvated by the water, okay? And there also there is a correlation between mass transfer coefficient and FFV or fractional free volume. That's how we, in our paper, that's how we discussed why after increasing zinc oxide ALD, TDS rejection rate decreased immensely. Here is the table, okay, for produced water and zinc oxide 40 cycles, or M2. M2. As you can see, after using this membrane, the treated water met all EPA requirement for drinking water and livestock watering. But for this case, we cannot claim it because the water, we did an analysis like for bacteria, organic chemicals, and heavy metals. In terms of TDS and TOC, we can claim this water is suitable for drinking water. Here is the performance of the proper membrane for produced water. Here is A and B. A is the pristine alpha alumina membrane before test, before separation test. B is the membrane after separation test. As you can see, a huge amount of contaminant is stuck on the surface of the membrane. C and D. C is the surface of the M6. I mean, after 120 cycles zinc oxide coating, and D after testing, after separation test. As you can see, if we compare M0 and M6, a less amount of contaminant deposited on the surface of the membrane, which means we could modify membrane in terms of anti-fouling property successfully. And again, in order to prove our claim, we did EDS test for M0 membrane and M6. For the yellow chart belongs to M6. As you can see, since here a huge amount of contaminant deposited on the surface of the membrane, EDS beam didn't detect alumina. But in this case, the alumina, since a less amount of contaminant deposited or fouling happens on the surface of the membrane, the beam detected the alumina surface. Here is the important index for flux recovery ratio. The higher flux recovery ratio, the higher anti-fouling property. Okay, how we can calculate this? First, initially, we run the membrane for 1 hour to calculate pure water flux, just pure water flux. Then we use the same membrane for treating produced water for 90 minutes, 1 hour and 30 minutes, okay, produced water. Then take out the membrane, trying to remove fouling and contaminant in order to try to regenerate the membrane, and then put it inside the equipment. And this time, again, we run pure water in order to calculate pure water flux. We call it the second one JW2 over JW1. Okay. And in this case, again, for all the modified membrane, FRR or flux recovery ratio is much higher than M0, which means we could give anti-fouling property to the modified membranes. Here is the last slide about we always need something regenerable in industry. In this case, we try to test regenerability of the membranes. First, for M0, after treating produced water, we try to remove the fouling, and then calculate the flux. But we got a negligible amount of permeate or pure water. That's why we could just run it for 1 hour continuously. And then for M1 the treating process increased to 2 hours. And for M2 to 3 hours, M3 3 hours, and for M4, M5, M6, we got the best result. The filtration process reached 4 hours, which means this membranes M4, M5, and M6 showed the best performance for regenerability. Here the conclusion. The contact angle measurements showed that the oil contact angle increased from 165 for M0 or alpha alumina support to 170 for zinc oxide ALD membranes with 120 cycles. TOC rejection and TDC were 96 and 300,000 ppm roughly for M0, and 99 and 10 ppm for M5. Pure filtered water or clean water met all the EPA requirement for agricultural purposes, especially for irrigation. The reusability and longevity of the zinc oxide ALD membranes was enhanced in comparison to the alpha alumina support. Thank you so much for your attention. I need to always, thanks my advisor for all his support, and also Dr. Dave and physics department, because they helped us to modify to fabricated membranes. Thank you. And I'd be more than happy to take your questions.
Very good. Thank you very much. Any questions?
Okay.
So what are the next steps with this, with the membrane and with this technology? Where do you go from here?
That's a really good question. First of all, we have a problem with the price. Okay. First, we could treat produced water by taking advantage of the liquid nitrogen. Okay, my advisor and I, especially my advisor, we are trying to make it more feasible, more cost effective. So rather than liquid nitrogen, we are trying to take advantage of solar energy in order to provide energy to evaporate water. So right now we are trying to make it practical. It's practical, but make it more economical, cost effective for industry. That's our next step.
Speaking of industry, are you working with any industry or working on getting this patented, or kind of how are you working on getting that, where it's more?
Yeah, we have collaboration with TDS, Technology Development Center, TDC. Yeah.
Okay. Very good.
And yeah, and also we have a really great collaboration with IX Power in industry, and we are holding monthly meeting with them about this technology. Yeah.